All right, it's time for our fourth and final sampling distribution. The sampling distribution for differences in sample means. We have done proportions and difference in proportions, and we have done means, and now we're going to do difference in means. But before we get into that, let's review last time. We talked about sampling distribution of the sample mean, and let's talk about the highlights from that. So here's a distribution. The distribution of ages in the U.S. looks something like this. It kind of starts out high, a lot of young kids around. There's a couple peaks here and there for different reasons. The birth rate's been high during certain years. And then it kind of drops off quickly. Not many people over 90 around. But this distribution, it has a mean somewhere close to 38.5. These are just quick numbers off of Google. I'm not sure how reliable they are, but let's talk about the population as a whole. The center the mean of this distribution of the whole population, mu stands for population mean, is 38.5 years. The shape, I would say it's got a little bit of skew, maybe bimodal. It's definitely non-normal. Let's just go with that. Skewed right, bimodal. There, it starts out kind of consistent. It's just an odd shape, the kind of shape that you get when you really do look up data. And the spread, I'm not sure how reliable this is either, but let's say the standard deviation is 13. And I just want to have a number to use. Not sure, again, if that's really accurate. I don't know how accurate any of this is, but it should be something close to that. So this is everybody living in America right now. We have a center of 38.5, a spread, a standard deviation, that's lowercase sigma standard deviation of 13, and a shape that's definitely not normal. So the point of the last video was, what happens if we, instead of looking at every single individual, what if instead we take a sample of 50 individuals at a time? This is called a sampling distribution, a list or a distribution of every single possible sample of 50 from the millions of people in America. See, you couldn't really take all of those samples, but we can know what that distribution would look like. So first main idea is its center. Its mean, which we would call mu sub x bar, that's the mean of all the little individual sample means, is equal to mu. So we have three individual means going on in this one formula. Mu, the first mu is the center of this next graph I'm getting ready to draw. X bar is all the individual means of all of our different samples. And mu is the mu from the first distribution. All this means is our center is not going to change. If we really take a random sample, then our sampling distribution will be unbiased, meaning it's going to gather around 38.5. So I would say mu sub x bar equals 38.5. What about its shape? Its shape is going to be approximately normal. How is that true? Well, our population is not normal. However, our sampling distribution is of samples of size 50. As we talked about, as long as that is 30 or more, the sampling distribution will be normal. This is called the central limit theorem. This is what allows stats to happen, to be honest. The central limit theorem says as long as you take samples of size 30 or more, any shaped population will become normal if you look at it 30 or more at a time. The sampling distribution will be approximately normal if we have 30. Now, if the population were normal, it wouldn't matter what our sample size was. But if our population is not normal, then we need a sample size of at least 30. So now I'm getting ready to draw a bell curve here. So to draw that bell curve accurately, let's talk about the spread. What is the standard deviation? The standard deviation of the sampling distribution of the sample mean, sigma sub x bar, so the standard deviation of all of our little individual means, is equal to the original population standard deviation divided by the square root of n. That's why I wanted to give you that 13 up above, so we would have a starting point. So basically, as your sample size increases, your curve gets narrower, your standard deviation gets less. And it's by a factor of the square root of n. So I would take my 13 and divide it by the square root of 50, and I would get 1.838. Let's just call it 1.8. So when I draw this normal curve down here at the bottom, my normal curve should be centered at 38.8. It should be bell-shaped, and it should have a spread of a standard deviation of about 1.8. If I multiply that by 3, that is about 5.5. And that tells me that at 44 and 33, I should have basically covered everybody. So my graph got really narrow here. 33 to 44 is going to be the entire bell curve. Almost. Remember, 3 standard deviations to the left and 3 standard deviations to the right pretty much includes everybody in a normal distribution. Not quite. Now, does that mean everybody in the country is gathered from 33 to 44? No, it means that if you take a sample of size 50, it is very difficult for the average age of those 50 people to be outside of the range of 33 to 44. Actually, it's probably more like 38 to, 39. Maybe 37 to 40 would be most people, according to the 68, 95, 99.7. But almost everybody is going to be 33 to 44. Almost every sample, I should say. So that's what we talked about last time, center, shape, and spread. When we stop looking at all the individuals, we start looking at samples, in this case, samples of size 50. So let's extend that, as we did with proportions, and talk about comparing two groups with their own unique center, shape, and spread. Okay, so let's look at two individual states. So let's do Kentucky and Florida. I'm using Florida. I'm, again, making up some example data, assuming that the ages in Florida are a little bit older than they are in Kentucky. I looked up these averages. I think this 38.6 and this 42.2 are fairly accurate. A lot of people retire in Florida, so in general, the age should be a little bit higher. And it looks like it's about 3.5 years on average, larger than it is in Kentucky. Just an example to play with. So here's the situation. We're going to sample 50 from each state, and we're going to subtract those two and find the sampling distribution of the differences in the sample means. All right, just like there's millions of possible ways I could sample 50 from Kentucky, there's also millions of ways I could sample 50 from Florida. And if I subtract all those possibilities, we create a sampling distribution for the differences. So let's talk about what that distribution would look like. First of all, it is going to be centered mu x bar 1 minus x bar 2. That's the average of the differences of the means of all the possibilities of those two samples, is equal to mu1 minus mu2. All that means for this particular example is if I subtract Kentucky minus Florida, my sampling distribution is going to be centered right where you would think it would be, which is negative 3.6 on this graph. Okay, that's because the difference in the actual means is negative 3.6. I'm doing Kentucky minus Florida, so my smaller mean minus my larger mean. It's going to be centered right where it's supposed to be. And that's the 4th time that's happened. What about the shape? This is also, it's really the 2nd time this has happened. Normal, and I always forget and I should always remember, approximately normal if N1 is at least 30 and N2 is at least 30, or if populations were normal. But if I've got a sample of size 50, it doesn't matter. I don't even have to worry about the shape. These shapes are not normal. They're not crazy skewed, but they're not normal. And so my sample sizes are both 50, so I'm good. I know I'm going to be drawing a normal curve down here. I'm going to go ahead and sketch in the normal curve. What about the standard deviation of my new curve that is made by mean minus mean? Okay, this is kind of a crazy looking formula, but it's not so bad. It's probably not as bad as the one for proportions. Sigma sub x bar 1 minus x bar 2. Of all of the different ways that we could take two samples and subtract them and add to this graph, what is the spread? The spread of this approximately normal curve is the true standard deviation 1 squared over the sample size 1 plus the true standard deviation 2 squared over sample size 2. Your two samples don't have to match, by the way. A lot of times you'll do 50 from each state or something like that, but it doesn't have to be that way. So this formula, which as all these formulas are, is on your formula sheet that you will have during your exam. This gives you the spread, or the standard deviation, of the sampling distribution of all possible combinations of a mean of 50 Kentuckians minus a mean of 50 Floridians. If I put our specific numbers into that formula for this example, I would get standard deviation equals, this is for x bar Kentucky minus x bar Florida, the square root of 13 squared over 50 plus 14 squared over 50. Because remember, my two population standard deviations were 13 and 14. When I put that in my calculator, I get about 2.7, and that tells me how far I have to go out for outcomes to be less and less likely. We always need this standard deviation. So if I wanted to ask a question, what's the probability that the difference in these two ages would be whatever, then I will do, let's just say, what's the probability that you take a sample of 50 Kentuckians and 50 Floridians, and the Kentuckians are actually older. So that's that zero break-even point that we see a lot. School's out. So this curve is centered at negative 3.6. We're looking for 0. If we add 2.7 to negative 3.6, you get negative 0.9. And if you add 2.7 again, you get 1.8. So the break-even point is about right here. And so for the Kentuckians to be older, we would have to get a positive result. So we're looking for that right there. So that would be normal CDF. 0 to infinity. Just a bunch of 9s will be good enough for infinity. On a curve that's centered at negative 3.6 with a standard deviation of 2.7. All right. I'm going to leave that one for you so we can cut this off and leave this video as short as possible. But this is our final sampling distribution. The difference in sample means. Where will they be centered? They will be centered at the true difference of means. What will the shape be? It will be about normal as long as the sample sizes are big enough or the populations were already normal. And what will its spread be? Its spread, its standard deviation will be according to this red formula. If you put all that information together, you can answer probability questions like that.